Hey guys, we got another statics problem here. Today we're doing a problem with internal forces, and we're given this truss with a distributed force on one end over here, and then we've got a single 6-kip force over here, and they want us to find the shear and bending moments and draw a diagram on a graph of that. And then we can afterwards find where the absolute maximum bending moment and shear forces are located on this beam. It's important you can find out where it would break first. So maybe you already know, but I'll just draw it out. If you take a slice right through here of this, we can draw in three forces. We've got the compressive or tensile force, we've got a bending moment, and then we've got our shear force. So that's our M. Shear is represented by a V for some reason, so that's how you'll see it. And so we don't care about this compressive force. There actually there's nothing happening in the x direction. We want to know our V and our M. And so what we do is we come up with an equation for V of x along this line, and at each of the supports it would change. So you'll end up with a piecewise graph. From A to C you'll have one thing, and then from C to B it'll be something else. And then you do the same thing with your bending equations. So first thing is we need to find the reactions at the supports A and C. Excuse me. It's an orange. Now we'll take the moment about A, and it's crappy A. So we know this distributed force can be said, since it's a rectangle, to act straight down the middle, and it is a 2 times 6, 12 kip force at 3 feet. So got negative 12 times 6 and minus 6 times 8 plus the reaction at C times 6 equals 0. Okay, so reaction at C equals 14 kips. And so we'll draw this up. 14 kips. And then we can use our sigma Fy equation to say, well, we've got 12 kips down here, 6 kips down here. That's 18 down, and we only have 14 going up. So that leaves 4 kips up at A. Okay, all makes sense. Now we can go and write an equation for what we would say our V and our M are. So there's a weird convention that negative shear forces are positive. So let me show you what I'm talking about. So we've got our bar here. I'm cutting it off before we get to the support C. Okay? So we've got 4 kips up here, and then all along here we have our distributed force downwards. So do a different color. So something like that. And so we say we've got 4 kips minus 2 times x feet. So minus 2x. And that's what the forces acting on the beam are. And if we were to switch this convention around, we would end up, since the negative v is positive. Okay, so this is what the forces are. That's f of x from a to b, a to c. If we wanted what the shear force was, we would just multiply this by -1. So v of x is 2x minus 4. And so as long as we're on this section of the beam moving from A up to C, not at C, but up to C, this equation will give us what the shear force looks like. So moving from C to B, we'll have a new equation. We'll have this total amount of force over here, and then however close we are to the 6. So if you think about it, the picture that we draw when we graph this, since as you move along this bar, the distributed force continually adds more and more force to this beam, what this is going to look like a slanted line. And since there's nothing over here adding as you move, then we'll have it'll be constant from C to B. But we still need to come up with that constant. So if you just add this all up, you see that 12 kips down plus 4 kips up is 8 kips down plus 14 kips up is 6 kips up. Okay? So when we're moving from this section over on the bar, but we haven't yet got to B, there on this side we have 6 kips acting upward. So this whole area has the same a constant amount of 6 kips of shear acting on it in the positive direction. And so v2 of x equals 6. Now we can make a rough sketch of that. It says oh no, this is wrong. Don't multiply it by -1. 4 minus 2x. So we start at 4 and we go minus 2x, and we take this until x equals 6. So when x equals 6, this is -12. 4 minus 12 is -8. So we end up at -8 down here. -8. We started at 4. Okay. This is shear versus length. And then after 6, from then on we have a constant positive 6. Or yeah, after 6 feet, we then on have constant 6 kips moving for the final 2 feet. I hope this makes sense. So at this point is where our shear changes from being more affected by this 4 to being more affected by the distributed forces here. And this is our 6, this is our 8 feet. Okay, now the cool part about what happens next is that when we go to find our bending moment, we can find the moment as a function of x, just in the same way that we found our v of x, or we can realize that the bending moment, that v equals dm dx. And so we can find our bending moment by calculating the area underneath our function, our v function here, which I think is easier. It might not be possible if it's something more complicated, but we can find it, and we'll just do that. So this is 1 right here. So this is 2. Yeah, because 4 minus 2 times 2 is 0. So this is 2 feet. 2 times 4 times 1/2 is 4. Okay, now from 2 to 6 is 4. 4 times -8 times 1/2 is -16. Alright, and up here we've got simply 6 times 2, so 12. Okay, we'll go down here. Let's change colors first. Make this guy a little bigger. Okay, so we want to find what the bending moment is from 0 up to 6 feet first. And so I'll mark 6. And then it ends at 8. And since at the ends there's no moment here, there's no moment here, we want, or that has to be 0. So there's 0 at both ends. So we know that this ends at this 0 and begins at this 0. And we also know what our first equation is. V of x equals -2x plus 4. So our m of x should equal the integral of -2x plus 4 dx, which is -x squared plus 4x. Alright, and set that equal to 0. X, and then 4 minus x. You get that there's a 0 at 4. So 4 here, and since this is negative, we know that it goes up. So our parabola here can look something like this. And then what happens at 6? Approaching 6, we'll have -36 plus 24. So we'll have -12. Okay, so we'll take this all the way down to 12, or -12. Alright, and we want to know at this point, because they ask, well, we might want to know that point. Well, that is halfway between 0 and 4, which is this 2. So our cleaning lady's here. 2. And we punch 2 in here, we get negative 4 plus 16, so 12. Or no, negative 4 plus 8, so this is 4. 4. And from here, this 6, this is at point C. So from then on, we have a constant 6. Well, yeah. And what I'm going to do is I'm going to say v of x equals 6. So the integral 60x equals 6x. Alright. So this might not be to scale, this should be a little steeper, but our slope here is positive 6. Okay, and then we know it ends at 0, so, or at 8 it goes to 0. So this is a graph of our bending moments. And we have, I just think it looks better like this. We have a maximum at 4 and a minimum at negative 12, but they want the absolute maximum of both of these. So we would have one right here. The absolute maximum value for our shear force is 8 kips. And the absolute maximum bending moment is 12 kips per foot, kip feet. Okay, and so our maximum shear happens at 6 feet. Our maximum bending moment happens at 6 feet as well. And that's it. So the key to remember here is that you can get back and forth from your v to your m by integrating v to m or differentiating m to get to v. Alright.